avec vous. Donc, bonjour à tous, je suis Victor Truong, responsable de la société EDA Expert et je suis très content de vous accueillir pour cette démonstration, pour cette présentation sur le produit du mois. C'est l'opération marketing qu'on fait régulièrement pour promouvoir justement l'un de nos logiciels, l'une de nos solutions. Et vu la température actuelle au niveau du contexte climatique, je crois que c'est important qu'on fasse un point sur notamment notre solution simulateur thermique qui s'appelle TRM de l'éditeur Adam Research. Donc, cette démonstration, cette session durera jusqu'à 11 heures. La présentation durera à peu près une demi-heure, 35 minutes. Et bien sûr, on vous laissera la liberté de nous poser des questions sur les choses sur lesquelles vous n'avez peut-être pas compris ou sur lesquelles vous souhaitez approfondir. Mais peut-être avant d'attaquer directement à la présentation des solutions logicielles, pour ceux qui ne nous connaissent pas ou moins bien, je rappelle rapidement nos trois activités dont la société EDA Expert est une société française, créée en 2012. On est basé en région parisienne. Nous avons donc trois activités. Activité de représentants. Nous représentons 13 éditeurs logiciels en France. Distribuons à peu près une vingtaine de solutions logicielles. Ça va de simulateurs thermiques, dont on va parler un peu plus tard. Il y a aussi des simulateurs de compatibilité électromagnétique, les calculateurs de MTBF, calculateurs de l'impédance. Visualisateur universel des fichiers de fabrication ainsi que la conversion des fichiers de fabrication. On fait aussi pas mal d'analyses DFM, Design for Manufacturing, en amont et en aval. Enfin bref, tout ce qui concerne la conception de cartes électroniques. Nous avons aussi des éditeurs et des solutions logicielles autour de FPGA pour visualiser les IP, des fichiers code, pour débugger les applications FPGA. Nous avons aussi des solutions pour la conception des solutions logicielles avec notamment ta signe BIOA, notamment pour pouvoir compiler, simuler, débugger et vérifier le respect des contraintes timing dans un système multicore. Donc, en fin de compte, on est un véritable distributeur de solutions logicielles. Parallèlement, nous sommes aussi organisme de formation certifié Calliope depuis peu et référencé bien sûr dans la base de données Datadoc, dont on propose des formations métiers, notamment sur la conception avancée des cartes électroniques, sur l'aspect thermique, sur l'importance de DFM. On fait aussi pas mal de formations sur les différentes solutions logicielles, notamment les solutions logicielles qu'on distribue, mais aussi on est partenaire de la solution Altium pour notamment donner des formations sur l'utilisation des solutions Altium. Et enfin, troisième activité de la société EDA Expert concernant tout ce qui est accompagnement. On réalise des prestations sur la simulation de l'intégrité du signal avec Hyperlinks, Security, ICD. Nous réalisons aussi des analyses DFM pour des clients qui en ont besoin ponctuellement. On réalise aussi des expertises, notamment sur la conception de cartes, notamment des cartes comportant des signaux rapides. Voilà, sans plus tarder, voici donc la liste des éditeurs qu'on représente. Et pour le mois de mars, donc on focalise sur notre partenaire éditeur qui s'appelle Adam Research, qui propose le produit principal qui s'appelle TRM, comme Thermal Risk Management. C'est donc une solution logicielle dédiée simulation thermique et principalement concernant au niveau de la carte électronique. Donc, cette démonstration cette présentation va être faite par l'éditeur lui-même, Johannes, en anglais. Johannes, can you hear me?
Yes, I hear you.
Okay, so I will stop sharing screen. Now you can share your screen, please.
Okay. Can you see my screen?
I can see your screen.
Okay.
You can start.
I can start. So, hello, everybody. Thank you for participating in this demo. We are talking about printed boards, temperature, but also about current and voltage and watts and so on. TRM is a type of software dedicated to simulate the thermal behavior of printed boards. It's thermal risk management. And you know that the temperature is always limited either by the board parameters or by the silicon and junction temperature and so on. Maybe you think it's easy because we have data sheets, but it's not easy because the data sheet does not represent your special PCB, neither the stack up, nor the layout, nor the distribution of components and so on. So even if we have identical heat sources on a board, we get different temperatures depending on the local environment of this component and the local heating and the local cooling. So a data sheet is never representing your board. What can we do? Of course, we can simulate and calculate. And because it's a board simulation, we rely on the standard files to receive the data. And the standard files are the Gerber files, the drill files. And for the components, we are using IDF, but you can also draw your own components using your mouse. And for the net list, we have different ways. For example, the IPC format 356. And you can feed in CSV and ASCII files and so on to create non-standard stuff. Using the Gerber is not sufficient. We also have to supply physics data. For example, the watts of the components or the amps in the nets and so on, but also ambient conditions. So what is the ambient temperature of the board? What is the heat transfer from the surface of the board to the ambient? Is it standard air cooling by free convection, or do we have a fan with a certain fan speed and or air speed and so on? And at the end, you get a result, of course, the temperature. But if we use amps to heat the traces, we also get a voltage or a distribution of the potential, the electric potential, and we get the current density. And from the current density, we get the heating. And the heating is giving some temperature. Of course, watts and amps can be combined. That's okay. Yeah. If you are user of the Altium Designer, we can offer an almost two-click solution, an export click from Altium to some intermediate file, and an import click, we call it a wizard, to get your data into the simulator. If you don't have Altium, you have the choice to create everything manually, which is not so difficult. If you are a little bit experienced, it's done within some seconds. If you know how to script, then you can create some template files, standard files, which you can then import with 1 click or 3 clicks. This is quite easy. What are we talking about? We are talking about a flat geometry, a printed board. And the printed board has, of course, a layer stack. Those data and the layout is coming from your design software. We have components on top, maybe components embedded, which may carry or which may create heat or not. And we have some sort of component or pads which we can use to feed in electric information. So we have a positive pin or pad and a negative pin of pad or pad, and both are connected by the layer copper, or the copper in the layers, and electricity can flow in this direction and is creating heat along its path. There are of course, drilled holes, either plated through holes or blind or buried vias or non-plated through holes. The number of drilled holes does not matter. I've seen models with 30,000 drilled holes. Additionally, we can do something for the cooling. For example, if the board is mounted on a wall or on a heat sink or a water cooler, then just add an adhesive to create an electric insulation and of course some thermal barrier, and assign the wall of a fixed temperature. Or if you know, if this is a heat sink, you can add the thermal resistance of the heat sink to parameterize all the fins, etc., without having need to import mechanical cut files, for example. You can also add something inside yourself, bus bars, to increase the local width of it or height of a trace. And you can, of course, bring some heatsink or parameter of a heatsink, the thermal resistance, on any component and so on. Okay, that should be enough as a preface. I will now show you the software with 2 or 3 different use cases. So for the Altium user among you, I've looked for a test piece, and I found, for example, this one. It's an Texas Instruments evaluation board with some MOSFETs here and obviously some fat traces or bars to carry a high current from this connector somewhere to the MOSFETs. So I will not go very deep into details. It's just a test case. And my test case poses the question, if I have, for example, 12 amp on this connector, and I will allow the current go this path here to those MOSFETs, yeah, what will be the temperature, or what can we expect as an effect of the current heating? Yeah. What we need is, of course, an Altium project. And now the easy part is we have a button here, TRM. And when I click the button, it's exporting everything we need. But if you want to do it, you can also add some parameters in the schematics. For example, we can assign the 12 volt to this connector, 12 amp, sorry, and another minus 12 amp to one of those MOSFETs. And that can be done in the schematic. For example, if I use the gate driver, here you see connector number 9, and it's got a parameter. The parameter name is called TRM, and the value is 1 for pad number 1 and 12 amp for the data. And you see it here in the parameter list. Just add a parameter and you know what to do. And we have to have a counterpart, minus 12 amp. And the minus 12 amp, I just deliberately used this component, U16. And you see pad number 3, which is connected to this net of VDC minus. It's getting 12 amps. Yeah, it's just minus 12 amps. It's just an example. In addition, I can add also a power value in watts, and this value should be 1.4. Yeah. Everything can be modified, deleted, and changed in the TRM simulator. This is just one way of delivering data. Okay, now we go back to the piece document and say TRM. What you see is a script developed by us, which is starting an out job plus some extra work to export these parameters, to export the netlist and the placement of the components, etc. Okay, now it's done. And we can start and open the TRM simulator. I start the import wizard, Altium. I use all the defaults, so don't worry. It's not a training. I have to enter a name for the project. It's reading all the Gerber files. It's also converting all the Gerber files. And at the end, it's done. Don't worry about this very tall buildings, the components. We have an expansion factor of 5 by default, so that we can easier look into details of the layers. So this is the import of the top layer. Then we see the bottom layer and so on. Yeah. We also identify the drilled holes. We have in red the plated through holes, in black the non-plated throughs. There's no blind and buried or back drills here. And we have, of course, the dielectric in between. And we have the components, but not only the components, this gray stuff. We also have colored pads. For example, yeah, I will show you in another table. Here we have one. Here we have this green pad. The green pad is part of the plus 16 volt GPS net, and it's connected to component D4 and connector number 2. And of course, this pad can be carrier of electric values, and the gray parts can be carrier of watts thermal information. Okay, now let's have a look what else is imported. So first of all, the size of the board. Yeah. Then we have the layer stack. When I imported first, I didn't recognize something, but now I know what's a little bit strange. You see that the thickness of the dielectric number 1 or level number 2 is 1.5 microns. This is quite unusual. Yeah, you would expect this to be 1.5 millimeters, and this may be 254 millimeters. But that's not a bug. It's part of the export. If we go to tools, no, design, layer stack manager. You see that the first dielectric is 60 mils, yeah, which is more or less this value. Okay, I don't say it's a bug, but we can repair everything here, and you can change what your import whenever you want. And you can try and play with all the data to make a good thermal design. for your production phase. Okay, then we have the drill file, so I don't need to go through all the details, or each drilled hole can be touched, can be deleted, can be moved, and so on. At the end, what's interesting for us is what we call the loads table. And in the loads table, you see some interesting stuff. For example, the name of the components or the reference designator. You also see columns called watts, Celsius, amp, and volt. And I think you expect here to some value. Here, for example, the 1.4, remember we added the 1.4 watts in the Altium schematic for component U16, and that's the result of the import. And now I can do whatever I want. Either I accept the 1.4 watts or I say 0, yeah, etc. And then we scroll down, we see a list of pins, which are solid pins penetrating the board. And now we have pads here. The pads have a net name, a tilde, and a component name and a number. Yeah, somewhere we should have our values from the schematic, but there's an easier way. If I use some SQL, we have the -12 for the component, and we have the -12 import, but this is distributed over each pin, and unfortunately all the pins have the same name. That's a problem with Altium, but I can change everything here and say replace the 12 by a 1, and now we have 12 times 1 as plus amp and -12 as a minus amp. Now this is now a good selection. Otherwise, the software will tell you a warning that the sum of amps is not 0. Okay, that's all you have to do. And now we can go to the test phase. We can calculate something. First of all, we have to define the environment conditions. So let's assume we are in the lab and we have 25-degree ambient. And we go to calculate. And we can start the calculation. It will take, say, 1 minute to calculate. It's just a push button here. But of course, I prepared something for you. We can start, and then I come back after having shown other things. This we can do, of course. There is something special. Okay, and I start the calculation. Here's a log window telling you what's doing. And so on. It already calculated the heat created by the amps. It's 2.699 watts. You see it if and this 2.699 watts are now imposed into the trace, and it's heating the board, and of course not only the trace but also the board and so on, and the components. So while calculating the temperature, a short info about the non-Altium users among you. So for example, if you are an Allegro ORCAD user, it's no problem to import your data here as well, yeah? So first of all, you have to create the Gerber files yourself, yeah? And then you start, oops, sorry. Well, that's of course a demo effect. I did click the wrong button. Sorry. Sorry. So let's do it again. This is the ORCAD design. Remember, we are calculating in the background. That's why a little bit slower. So if you are starting from fresh, you go to Build Board, to the Layer tab. And what you then do is you say, create an empty template for n layers. And n in this case is 6. We have 6 layers. Or if you're able to script in ORCAD, you can create a template. The template is a text file with just this information you see here. Yeah, it's a comma separated file. And if you then select import template, it's filled automatically. Yeah. So this is then the result and so on. Same procedure for the drill files. If you always have the same drill files, or if you have a script, you can also, in the background, it's writing the results. That's why it's a little bit we have to wait. It will come in a minute and a second. The template you can create in ORCAD is, again, just what you see is what you get, and you have to convert or read the file, and then you will get the placement, etc., of all the drilled holes and non-plated, and the through holes, and so on. In that case, we have blind vias. Yeah, we have through holes between layer 1 and 6, and we have blinds between 3 and 4. Okay, calculation minutes. Okay, let me go back to this one. Now we can see the result. This is the result of the temperature. Remember, we are starting with current here and end here. This is a little bit strange in the top layer. Now we go into the board. It's always also a little bit hot, yeah, 260 degrees, which means that 12 amps is far too much for this trace. It's not a problem for the big parts of the trace, yeah, but here we have a problem, yeah, and that's why the thick part is in 3 layers, but the connection from here to here is managed in 1 layer, in the mid layer 1, and this is a critical point. Maybe it's easy to you don't think initially what could happen in your design, and that's of course a theoretical prediction. The quantity I'm showing here is the current density, the amps per square millimeter. And the amps per square millimeter in itself are not related to temperature. The temperature is created then using the copper around and so on, and the environment condition as a physics way of calculation. Okay, we also have the voltage here. You can calculate the voltage drop between this point and between sink and source. Yeah. For example, here we have a potential of 8.9. Don't say it's voltage, it's a potential. And we have a value of 8.8, which then is a voltage drop of 0.1 something volt or 100 something millivolt. This is the voltage drop along the path and so on. The temperature now has been calculated without the power of the component itself. What you have to do now is, of course, either reduce the current or to increase the thickness of the trace. Now let's have a look at the other examples. Here we have, what's this one? Let's have a look at this one. This is also a Texas Instruments test board, which is a little bit more interesting. No. What happens? Okay, we have here ground and VBUT, and we now feed in some amps into VBUT, but we make the MOSFETs and the shunts electric conducting, which means that the current finds its way through the components, yeah, back to ground. In addition, we can assign an electric resistance to these components, and by this we get a voltage drop, and we get a local heating for the MOSFETs and for the resistors. For the MOSFETs, I'm using the RDS on value from the data sheets. The resistance of the shunts is known, and for the current, I'm using an RMS current, so I'm using a DC approximation to this situation. And here you see what I was doing. What I can do is to reduce the factor here, so it's a little bit easier. So this is the origin of VBUT, this one. The current flows like this, going through the half bridges and then returning to ground. I can show you the results. For example, the flow of electricity. This is our starting point. And if you go to the top layer, we see that the current is escaping from the top layer. It's entering into this diode and then goes on, and it goes into the MOSFETs and out of the MOSFETs, and then it's returning to the ground. Yeah. You can also see the voltage drop. So we start with a high voltage value and end with a low voltage value, and the total voltage drop along this path is more or less 0.15 amp. Top layer. You see the change in color from green to yellow. We have a voltage drop according to the resistance of this component and according to the local current going to this, passing this transistor. Okay, what about the temperature? Temperature looks like this. The diode obviously has a high resistance, but also a very bad cooling situation, because those components have a complete circle, 360 to cool. This component more or less has a 180 circle, half circle, but it's also, the heat is also trapped in the design. Yeah, you see a sharp transition in temperature between this point and that point. And this is of course due to the local design. Yeah, the heat cannot jump from this point to that point because there's an insulation. And if this is a problem, you have to make this this region a little bit larger to allow for more heat spreading. What you else get is a report file where all the graphical data are in numerical form. It's a long list, but you then can identify how many heat is created where, or which amount of heat is creating which temperature. For example, we have a total heat flux of 3.1 watts. This is the electric heat plus the heat created in the components. Somewhere above, we see the heat created by level. Most of the heat is obviously created here in the top layer, 0.9 watts, and the rest in the other layers. And here we have a summary by net. There's only one net in this case. If you have more than one net, you will get the joule heating for each net, for example. Okay, what else to show? If you are a PADS user, it's the same procedure. You import your Gerber files. First, you prepare the size of the board. Then you import your Gerber files, you import your drill files, and add the current or no current, or the power of the components. And in this case, I have a test power of 1 watt to one of those components. And I quickly show the results. I think this guy here, ICL11 is getting 1 watt. You see it here, value 1 type watt. And the heating of the 1 watt component is giving rise to a temperature of 64 degrees in that case. 64 degrees in a 20 degree ambient, which means we have a temperature rise of 44 degrees, and divided by 1 watt, which means a thermal resistance component ambient of 44 Kelvin per watt. Now let's have a look at the temperature map. It's a little bit funny here, yeah. This corona type, sorry, of temperature distribution. But of course, this is an effect of the local design, yeah. If I look at the Gerber file, for example, or the imported Gerber file, we see in gold the copper traces, and the heat will follow partially the copper traces and then try to penetrate the FR4 and to escape to the air. We see it in the heat flux vector. Yeah, heat is flowing along the traces, maybe, and of course down, and of course up. And by this, you can identify maybe bottlenecks in your design if it's a critical point of temperature. What I didn't talk about is transient calculations. There is an option called transient. The standard transient is we keep all the watts and amps fixed and want to see the heating curve. Or in other words, how long does it take until some critical or reference temperature is reached in seconds? Yeah. If you don't want to have a permanent power or permanent current, you can supply a so-called cycle file, which is nothing more than an Excel file. And the Excel file is telling which component or which part has current or power in a certain period of time, or when does it start to increase or to reduce the power. And the result, of course, is a transient curve of the temperature anywhere in the model. It's done by using virtual thermal couples, which can be placed, and then you get a graph with the result. Okay, I think there is much more to tell you, but I'm looking at the watch, and it's 30 minutes now of presentation, and I think we would like to answer your questions and to proceed. Thank you.
Thank you, Johannes. It's time for you, c'est à votre tour. Donc j'espère que vous avez pu voir effectivement donc cette solution logicielle, ce simulateur thermique dédié carte électronique. Hein, c'est vrai que Johannes a commencé par utiliser Altium Designer pour montrer effectivement le côté PCB, la conception PCB. Il est évident que ça s'adresse aussi à tous ceux qui utilisent PATS, OrCAD, Allegro, peu importe. C'est un outil qui est universel, indépendamment de l'outil des CAO utilisé. Simplement, actuellement, on a quelques connecteurs avec ces outils, notamment Altium Designer, pour récupérer automatiquement les fichiers nécessaires afin de lancer la simulation. Voilà, donc est-ce que vous avez des questions? Est-ce que vous avez des choses sur qui vous n'avez peut-être pas bien compris? Vous avez le panneau discussion ou bien le panneau questions-réponses afin de pouvoir poser vos questions. Est-ce que ça vous a parlé? Est-ce que vous avez des contraintes au niveau de température? J'imagine si vous êtes là, c'est que vous avez sans doute des problématiques thermiques. On parle souvent de l'intégrité thermique. Pour ceux qui ne sont pas très habitués à écrire en français ou en anglais, peu importe, vous pouvez aussi lever la main afin que je puisse activer votre micro. Non, je ne vois pas de questions supplémentaires. Sinon, si vous avez envie de tester cette solution, ce logiciel, justement pour simuler l'aspect thermique de votre carte électronique, hein, on est à votre disposition. Vous pouvez nous contacter, nous sommes prêts. Hein, on est partiellement en télétravail, partiellement au bureau, comme indique notre gouvernement par le temps qui court. Vous pouvez nous joindre à ce numéro 01 58 07 00 79 ou bien nous écrire contact@eda-expert.com. Je regarde encore, est-ce que si vous avez des questions, des commentaires, non. Dans ce cas-là, je pense qu'on va arrêter donc cette démonstration en ligne et on reviendra vers vous individuellement pour prendre vos impressions, vos feedbacks, éventuellement des questions que vous aurez par la suite.